Hi everyone! Today is Friday, October 7th. So this week we don't have any quiz, but please keep working on your homework daily, okay? And if you have questions, you can either email me or you can post it on like this questions file. So some of you post these questions. So let's look at these questions. So use synthetic division to determine whether the first expression is a factor of the second. So we want to see whether this guy is a factor of the second one. If it is, indicates the factorization. Okay, so let's see. So synthetic division, right? So this factor x minus 1/2, it corresponds to the roots is 1/2. Right? If we use synthetic division, we put the roots 1/2 right here. And this polynomial, we put down the coefficients. So we have 2 x to the fourth, right? And then minus 1 x cubed. And do you see there's no x squared? So that's why we put 0 for x squared. And 2x, and then minus 1. Yes, everybody? Okay, and how do we do synthetic division? We move this down, and then we use it to multiply by 1/2. We get 1. And we add those two numbers, we get 0. And 0 multiplied by 1/2, we get 0. And we add those two numbers, we get 0. 0 times 1/2 is 0. When we add those two numbers, we get 2. 2 times 1/2 is 1. When we add those two numbers, we get 0. And this last number is the remainder. Okay? If remainder is 0, that means x minus 1/2 is a factor of the polynomial. Okay? So therefore, we can say this, let's say this is p of x. This polynomial can be factored as x minus 1/2, and then the quotient is, you read these four numbers corresponds to the quotients. Okay, that's why the last number is the constant term. So constant term is 2, and then this number corresponds to the coefficient of x. This number corresponds to the coefficient of x squared, and then this number corresponds to the coefficient of x cubed. Therefore, we have 2x cubed plus 2. Okay, everybody? So this is the factorization. So the problems say if yes, indicate the factorization. So you can type this into the box. So this is the solution of this problem. Okay? And if the problem asks you to factor further, okay, how can you factor further? Well, so this is beyond this problem, okay? So for this problem, you can just type here in the answer box, okay? But if the problem asks you to factor further or factor completely, then do you see the second factor, we have the common factor 2? So we can factor out the 2. We have x minus 1/2, 2, and x cubed plus 1, right? And next one, you can, so x cubed plus 1, if you can remember the formula of x cubed plus a cubed is x plus a times x squared minus ax plus a squared, and x cubed minus a cubed is x minus a x squared plus ax plus a squared. Okay, if you remember this formula, this is exactly this format where the a is 1. So therefore, oh, by the way, you can distribute these and then you will get integer coefficients. So 2x minus 1. And now this is x plus 1. And yeah, x plus 1. And x squared minus a is 1. So x plus a is 1. 1 squared is 1. So therefore, this is how we can factor it completely. And so you can see the roots. This is the 1/2. How about this root? -1. And this guy is an irreducible quadratic factor. Okay, irreducible means the discriminant, the b squared minus 4ac is negative, so you get 2 complex roots. Okay, so if you want to find those complex roots, we can use the quadratic formula. So x equals 2a, a is 1, so that's why the denominator is 2. Negative b is -1, so that's why negative b is 1, plus or minus b squared. -1 squared is 1, minus 4ac, but a and c are both 1. So that's why we get 1 plus or minus 1 minus 4 is -3. So that's why you can put square root of 3i. And so this is how we express the complex numbers. Okay, so this is a degree 4 polynomial, and you end up getting 4 roots. Each of them have multiplicity 1. And multiplicity, remember, that is the exponent of the corresponding factor. So all these have multiplicity 1. Okay, everybody? So for those of you coming late, I just answered a questions from your homework. So some of you post these questions on our question sheets. Okay, so if you want to see the solution, please watch the recording, okay, for those of you coming late. All right, let's continue. So last time we talked about how to graph rational functions, right? And here are the steps. First, we factor the numerator and the denominator. Second, we find the x-intercepts where we set the numerator equal to 0. And then we find the y-intercept by plotting in f of x is 0. Yes, that is the y-intercept. And then to find vertical asymptote, we set the denominator equal to 0. Okay, and after we find those numbers, we let x go to that number from the right, and we let x goes to that number from the left. And we see whether y goes to infinity or minus infinity. Yes? If yes, then we get vertical asymptotes. And vertical asymptotes are vertical lines. So you should answer an equation, x equals a number. Okay? Lines, equation, x equals a number. And then to find horizontal asymptotes, we don't look at the factor form. We look at the original form, and we look at the leading terms. The leading terms is the highest power terms in the numerator and denominator. Yes? So, and you let x goes to infinity and see what happened to the y. And you let x goes to minus infinity and you see what happened to the y. If y goes to a number, then we have a horizontal asymptote. Horizontal line. Y equals that number. So horizontal line is an equation. So don't just answer a number. It's an equation. Y equals that number. Okay, everybody? And finally, based on the information, you can plot the x-intercept. Okay, put the points there, and then you can plot the y-intercepts. And based on the vertical asymptote, you can tell it's on the left-hand side or right-hand side, up or down. So you can plot the small points over there, okay? And horizontal asymptote, for horizontal asymptote, we don't know whether the function is approaching it from the top or the bottom. That's why you put 2 points near it. 2 points near it. And then finally, you start near the origin and you connect all the points together. Make sure you have a function, which means you cannot go back and forth. So you cannot go here and then here. So that's not a function. It must be a function. So you cannot go back and forth. It must pass through the vertical line test. Okay? And then we have the, let's see. Right, and then you connect the points together. For these 2 points, you decide which points will make more sense. And then you can use that point. And then this one, the top point make more sense. So connect the top points and then erase the bottom points. Is that okay, everybody? I put a clause here. I want to let you know. We initially put the 2 points and then we erase it. Okay, everybody? Mm-hmm. All right. So now I want to make a comparison with you. So vertical asymptotes and horizontal asymptotes. Let's make a comparison. So for vertical asymptotes, they are vertical lines. Okay, vertical lines. So you will have x equals a number. That's vertical lines. Horizontal asymptotes, they are horizontal lines. Okay, horizontal lines. So y equals a number. And how about the number? So the number of vertical asymptotes, you can have 0, okay, vertical asymptotes, or 1 vertical asymptote, or 2 vertical asymptote, or 3. You can have as many as you want, okay, or infinitely many. So in the second half of the semester, we'll talk about track functions, and then we will learn tangent x. Tangent x has infinitely many vertical asymptotes. Okay, so the number of vertical asymptotes can be 0, can be 1, can be infinity. Okay, but horizontal asymptotes, okay, the number of horizontal asymptotes, it could be 0, it could be 1, and it could be 2, but at most 2. Because you can approach a horizontal asymptote when x goes to infinity. You can approach another one when x goes to minus infinity. But at most 2 different horizontal asymptotes. Is that okay, everybody? Mm-hmm. And then can we cross? So can we cross the asymptotes? Can we cross the asymptote? And for vertical asymptote, no. Okay, we cannot cross it. You might have a picture like this. You can have one side is getting close to it, but the other side you can have something like this. Okay, this is okay. You can have a piecewise function like this as long as when you're approaching it on one side and the y goes to infinity or minus infinity, then we say we have a vertical asymptote here. So we cannot cross it, but you can touch it. Is that okay, everybody? Mm-hmm. So this is okay. This piecewise function is okay. One side we're approaching it, the other side we touch it. It's okay to touch, but we cannot cross. Okay, everybody? So that is for vertical asymptotes. Horizontal asymptote, yes, we can cross it. So the picture is like, okay, maybe we have a horizontal asymptote here, and the function is like this. So yes, to this picture, we can cross the horizontal asymptote. Okay, you can cross it as many times as you want. Yeah. So that's horizontal asymptotes. And how do we find vertical asymptotes and horizontal asymptotes? Okay, how do we find them? We factor the numerator and denominator. So numerator and denominator. And then we set the denominator equal to 0. Okay, And let's say we solve for x and we get x equals to a number. Then you have to check when x goes to a from the right, what happened with the y? Do we get plus infinity or minus infinity? And when x goes to a from the left, what happened to the y? Would that go to infinity or minus infinity? So this is how we find vertical asymptotes. And then for horizontal asymptotes, we don't factor it. Okay, so do not look at the factored form. Okay, we look at the dominant terms. So dominant terms, which is the highest power term in the numerator and denominator. Okay. And what do you want to do? You want to let x goes to infinity and see what happened to y. Is y approaching a number? If yes, then we have a horizontal asymptote. And how about when x goes to minus infinity? Is y approaching to a number? So this is what we look at. Okay? So this is a comparison between vertical asymptotes and horizontal asymptotes. So when you learn some new concepts, not only in this course, maybe in other course, if you find some concepts are very easy to get confused, it's good to make a comparison. And then maybe have some examples next to it so you can see what the difference of the similarities. Okay, everybody? Mm-hmm. All right. Okay, so let's keep going. Example 4, I will let you to do at home. So as you know, we are behind schedule, so we are not able to cover all the examples in the class notes. But on our website, I give you the notes with answers, so you can see the answers on the website. But I hope you can try those problems first, and then look at the answers and fix your mistakes. Okay? So in that way, you can learn and practice. Math is really practice a lot. Yes. Okay, slant asymptotes or oblique asymptotes. So which are neither vertical asymptote nor horizontal asymptotes. This only happens when the rational function, if the degree of the numerator is 1. So degree of the numerator is 1. Sorry, it's 1 greater than the degree of the denominator. Okay, so last time we have the numerator and denominator. If the degree of the numerator is less than the degree of denominator, then we know we have a horizontal asymptote, y equal to 0. Yes, because your denominator is bigger. So when x goes to infinity, 1 over infinity is 0. Yes, everybody? Mm-hmm. And if the degree, okay, so if the degree of numerator equals the degree of the denominator, then we have a horizontal asymptote. Y equals A over B, where A is the leading coefficient of your numerator. B is the leading coefficient of your denominator, right? So, if the degree of the numerator is 1 bigger than the degree of the denominator, we don't have horizontal asymptote. We have a slant asymptote. Okay? How do we find slant asymptote? Use polynomial division. Use either long division or simple division. The quotient gives you the asymptotes. Okay? So because your numerator, the degree is 1 higher than the degree of the denominator. So that's why it guarantees your quotient is a linear function. Okay, everybody? So your quotient is a linear function. So quotient is a linear function. So you get a line. So that line is the slant asymptote. Okay. All right. So let's look at this example. Let me see. Okay. Where's this one? Okay. Let me see. Is it the same thing? Oh. Okay. Interesting. Why are my notes are different? Let's see. What's this? What's this one? Oh, okay. Interesting. All right, all right. Yes, that's right. Okay, I was on the wrong page. Okay, good. Okay, so let's look at this problem. We want to graph it. And so the steps are similar. Step one, we want to factor it. So how do we factor it? Can you factor the numerator? X minus 5 and plus 1. Yes. So first step, we factor the numerator and denominator. Right, everybody? Okay. And how do we find the x-intercept? We set the numerator equal to 0. So numerator x minus 5, x plus 1, set it equal to 0. Therefore, x minus 5 is 0 or x plus 1 is 0. What's x? X is 5. And this guy, x is negative 1. Is that okay, everybody? So our x-intercept is 5, 0, and negative, 0. So x-intercept, they're points, right on the point. Okay, how about y-intercept? Y-intercept is we plug in x is 0. So f of 0. Question, do you want to plug in the original form or the factor? Original, because when you plug in x is 0, all the terms with x are gone. So you're left with the constant terms. You see that, everybody? And if you plug in the factor form, you still need to multiply the factors. So yeah, put in the original form, we get 0 minus 5 and 0 minus 3. That's why negative 5 over negative 3 is 5/3. Y-intercept, they are points. So 0, 5/3. So far so good, everybody? Yes? And then we have vertical asymptote. Okay. So vertical asymptote, we find the domain, right? So we first set the denominator. So denominator. What's the denominator? X minus 3. Set it equal to 0. So x equals 3, right? Oh, when you say the domain, yeah, then the denominator cannot be 0, so x cannot be 3. And then you let x goes to 3 from the right. Okay, x goes to 3 from the right. Then that factor, x minus 3, will go to 0 plus. Is that okay, everybody? And y will go to, so we plug in x equals to 3. Do we plug in the original form or do we plug in the factor form? Factor form. Yes, very good. So we plug in the factor form. You see the numerator? 3 minus 5 and 3 plus 1. Denominator, x minus 3 is 0, but 0 plus. You see? 0 plus. It's very important if it's plus or negative, minus, right? Because 1 over 0 plus is infinity. 1 over 0 minus is negative infinity. It's like heaven and hell. Big difference. Okay, so a minus sign can make a big difference. So be careful. Okay, so 3 minus 5 is negative 2. 3 plus 1, 4 over 0 plus. What's the answer? Plus or minus? Oh, minus infinity. Yes. That's you. And then when x goes to 3 from the left, okay, we have x minus 3 goes to 0 minus. So y goes to, you see, negative 2 and 4 stay the same. But now 0 plus becomes 0 minus. So what is your answer? Positive infinity. Yes, everybody? Okay, so that is for the vertical asymptote. Vertical asymptote is the line x equals 3. Okay? And then the fourth one. The fourth one, usually what we did is horizontal asymptote. But do you see what's the degree of the numerator? 2. Degree of the denominator? 1. So you know 2 is 1 bigger than 1, right? So we do not have horizontal asymptote. We have slant asymptote. Okay? So that's why here we know we have slant asymptote. So we use synthetic division. Okay? So we know that we will have slant asymptote. Okay? And we know that because the factor x minus 3, right? X minus 3 is the divisor. So the root is 3. Do you agree, everybody? Yeah, x minus 3 is the divisor. Then the root is 3. So if you use synthetic division, we have the root of 3. Okay. Yes, the root is 3. And we use x squared minus 4x minus 5. So x squared x squared has coefficient 1. And then minus 4x, so negative 4 and negative 5. Yes, everybody? Synthetic division. You move the 1 down here. 1 times 3 is 3. 3 minus 4. Negative 1 times 3. Negative 3. Add them. Negative 8. Yes, everybody? So negative 8 is the remainder. Okay. So the quotient. This is the quotient. Quotient is what? X minus 1. So slant asymptote. The slant asymptote is y equals x minus 1. Okay, so this is how we find the slant asymptote. You might ask, oh, why? Why is that? Well, using the synthetic division, you get, so when we start with x squared minus 4x minus 5 over x minus 3, that is the quotient, and then plus the remainder over the divisor. Okay, wait, after the synthetic division, this is what you mean. This is the quotient plus the remainder over the divisor. Yes, everybody? And now you imagine when x goes to infinity. Do you see this is constant over infinity? This guy goes to 0. Yes, everybody? So, okay. So this guy, okay. This guy, when x goes to infinity, this guy goes to 0. That's why our function is approaching to the line y equals x minus 1. So that's why this is a slant asymptote. Okay, now how do we graph this picture? Okay, so first of all, let's put points. We have 5, 0. Okay, let's say 5, 0. Let's say 5, 0 is right here. And -1, 0. -1, 0. Let's put it here. Okay, so they are the x-intercepts. And then y-intercept, 0, 5 thirds. So 5 thirds here. It's over here. So, okay, those are 3 points. And then vertical asymptote. 3, let's say 3 is right here. We have a vertical asymptote. And when x goes to 3 from the right, so this is right hand side. Y goes to -infinity, so up or down? Down. So you put a little dot right here. Okay, so you put a little dot right here. And when x goes to 3 from the left, the y infinity, up or down? Up. So you put a dot right here. Okay? And now we have a slant asymptote. So this is something new. Slant asymptote, y equals x minus 1. How do we graph a line? Yeah, this is the slope-intercept point. You first draw the y-intercept. The y-intercept is -1. And then your slope is 1. That means you go to the right 1 unit, and then you go up 1 unit. And then this is the line y equals x minus 1. Is that okay, everybody? So rise over run. So you go to the right 1 unit and go up 1 unit. You get this point. 2 points can fix a line. Okay. So now we draw this picture, right? Because when x goes to infinity, we are approaching this line. Okay, so we're approaching this line, but we don't know which side. So you draw a pair of points here. And then here, we don't know which side. So we draw a pair of points there. Can you see the pair of points here? Okay, now let's connect the points. So from here, we connect. Do you see we should connect these points? Yeah. So we connect them. So let me. Okay, let's use this. We connect them. Do you see the top points make more sense? Yeah, that's why we erase the bottom point. So we erase the bottom points. So on your exam, erase the bottom point. Okay. And here, see, we have this point and connect with this. Then do you think the top point make more sense or the bottom point make more sense? Bottom. Yes. So we can connect those. So this is what the picture looks like. Is that okay, everybody? Yes? Maybe it's curvy, it's weird, but it should be more smooth. So it should. Okay, let me do it slowly. It should be quite smooth. Can you imagine, everybody? Okay, so this is the example how we find the slant asymptote. Any questions about this example? Are we all good? Yes, everybody understand? Yes? Okay, so here we have more exercise, but I will let you to do at home. And then I have the solution on the website. It's the notes with answers. So please check the solution. Okay. I really need your help because our course is only 4 credit hours, so I only meet you 3 times a week, right? And usually algebra, 3 credit hours, trig, 3 credit hours. So together should be 6 credit hours. So which means that I miss a lot of time. I want to see you more often so I can teach you more and we can do more examples. So, but we have limited class time. So that's why I hope I make more resources and post on my website, and you can use those resources. Okay, everybody? Let's try our best. All right. Okay, so this is a word problem, right? The game commissions put 100 deers into a newly acquired state farm park and park land. Okay, the population n of the deer is modeled by the following, where t is the time in years. Find the population when t equals 5, 10, and 25. All right, so part A, we plug in t equals 5, right? So that means whenever you see t, we place t with 5. So t is 5. 1 plus 0.04 times 5. Is that okay, everybody? So you plug this in your calculator. And, well, you see, 3 times 5 is 15, plus 5 is 20, right? This is 20. 20 times 20 is 400. And 0.04 times 5 is 0.2, right? And plus 1, 1.2. So you put this in your calculator, you get, what do you get? Yeah, thank you. Right. Okay. Oh, because this problem, we're talking about the number of deers, so it should be whole number. So we just use 333. Yeah. Okay. And then how about when t equals 10? So you do the similar things. Whenever you see the t, we place t by 10. So that's why, okay, numerator 20 times 35, and this is 1.4. What do you get? Sorry, what do you get? 500, thank you. So we get 500. All right. And what happened when t equals 25? So we plug in 25 plus 3t, but t is now 25. Over 1 plus 0.04 times t. T is 25. So what do we get? We get 800. Okay, so yeah, put those in your calculator and then you get the number. Okay, so part A is easy, right? We plug in the t equals those numbers to evaluate the function. Part B, what is the limiting size of the deer times as time increases? Okay, as time increases. Oh, where's my S? So as time increases, what happens? Okay, well, that is the same as saying we want to let t goes to infinity. And remember, when t goes to infinity, you look at the dominant terms. Yes? So we look at the dominant terms. Dominant terms is the highest power terms in the numerator and denominator. Look at your numerator. What's the highest power term? Do you see is 20 and then times 3t? Yes, do you see that? Dominant term is 3t, but because it's multiplied by 20, so you cannot miss the 20. And denominator, do you see the denominator is 0.04t? Yes. So, oh, t cancel. So this is like 60 divided by 0.04. What do you get? Thank you. So that is the limiting size of the d's. Okay, when t goes to infinity, what happens? You look at the dominant terms. Okay, any questions about rational functions? So we learn how to draw it. We learn vertical asymptotes, horizontal asymptotes, and slant asymptotes. By the way, if the degree of the numerator is greater than the degree of the denominator by more than 1, then you just say we don't have any horizontal asymptote or slant asymptotes. Okay? Yes. So when your x goes to infinity, your y might go to infinity or minus infinity, and your x goes to negative infinity, maybe your y goes to infinity or minus infinity. Okay? So it depends on the picture, and then you know that. Okay, very good. So that is 3.7. So I hope for those problems I will let you to do at home. Okay, please work on those and uh, uh, check your answers on the website. And for those of you coming late, we solved this problem. So some of you post these questions on the question sheets on the website. So we solved this problem. So if you come in late, please watch the recordings. Okay, yeah. All right, so today we go back to chapter 1.7, inverse functions. So some of you asked me before, hey, we have the 1.7 homework. Why we didn't cover 1.7? Well, because the next chapter is chapter 4. We will talk about exponential function and logarithm functions. They are inverse functions. So that's why I move the inverse functions here. So then after we finish the inverse function, we can talk about exponential function and logarithm function. You have a fresh memory about the properties of inverse functions. Okay. So inverse function. First of all, a function f of x is said to be 1-to-1. Oops. Okay, 1-to-1. If f of a is not equal to f of b, whenever a is not equal to b. In other words, whenever different inputs give different outputs. So that is 1-to-1. Do you remember that we have, what's that? Okay, so this is the vertical line test. Okay, vertical line test help us to figure out if this is a function, right? If every vertical line just intersect the graph at most once, then this is a function. For example, this is a function, but this is not a function. Yes. And horizontal line test. So horizontal line test help us to figure out whether a function is 1-to-1. Okay, for example, this guy is not 1-to-1 because see that line intersect the graph twice. So that is not 1-to-1. But this one, like the x cubed, this is 1-to-1. Okay, so vertical line tests help us to figure out whether a graph is a function. Horizontal line test help us to figure out whether a function is 1-to-1. Therefore, is this guy 1-to-1? No. Yeah, you use any vertical horizontal line to intersect it, and we get 2 intersection points. So this is not, okay, this is not 1-to-1. Okay. Yeah, so virtual way to determine if a function is 1-to-1, we use the horizontal line test. Yes, so we talked about those before. Okay, are those functions 1-to-1? Is this 1-to-1? No. Is this 1-to-1? Yes. Is this 1-to-1? No. Easy. Yeah, everybody? Okay, very good. Alright, so now inverse function. So let's say we have a function f. It maps the x values to the y value. Let's say this is x, this is the y, and this is the domain of f. This is the range of f. Okay? And so let's say this function is f of x is 3x minus 2. So that's why when you plug in 4, okay, when you plug in 4, you get 3 times 4 minus 2. 3 times 4 is 12. 12 minus 2 is 10. So it maps the 4 to the number 10. Yes? Then how do we undo, okay, what f did to the 4? So can we map the 10 back to the 4? And this is called the inverse function. So we want to do the reverse order, okay, reverse operations so that we can map the outputs, okay, and back to the input. So we call this is the f to the minus 1. So this is the inverse function. And now you see this is the domain of the inverse function. And the domain of the inverse function equals to the range of the function. And your range of the inverse function is now the domain of the original function. Okay, everybody? All right, so yeah, this notation f to the negative 1 is called the inverse of f. Be careful! This is not reciprocal. So this notation is the inverse function. It's not 1 over f. This is not the reciprocal. Okay, everybody? So be careful of that. Okay, so main properties of the inverse function. If f of a equals b, so f mapped a to b, then f inverse mapped b to a. Okay, the domain of the inverse function is the range of f. The range of the inverse function is the domain of f, because they kind of switch the input and the output. So the x and y, the row exchange. Okay. And for all the x in the domain of f, we have f inverse composite with f equals to x. And why is that? You can think of, okay, so you have x. Let's say this is y. So this guy means we first do f, okay? We first do f first, and then we apply the f inverse. Do you see? We get the x back. Yes, everybody? Or and this picture, okay. This picture, if you say this is y, I know the notation is a little bit. I think maybe it's better to look at, okay, f composite f inverse y equals to y. Yeah. So if we look at this means we start with the y, and then f inverse y, we get the x. And we map the x back to the y. So you start with y, and then you apply f inverse, and then f, you get the y back. But you can call the variable any letter. You can call it x, a, b, c, d, up to you, right? So that's why they mean the same thing. So inverse function, when you apply the inverse function composite, remember this little circle means composition. It's not multiplication. Remember that from your exam? That is composition, not multiplication. So yeah, you do composition, you get the variable back. And okay, consider the functions given by the table. Find a table for f inverse. Well, f inverse is like you switch the inputs and the outputs. So, which means these were your outputs. Now you put them into the inputs. So you put 11, 8, 5, 2, minus 1. Okay? And those were your inputs. Now you put them in the output. Exactly. So negative 2, -1, 0, 1, 2. Okay? So our f maps -2 to 11. Then our f inverse map the 11 to -2. Is that okay, everybody? So inverse function, switch the x and y. Okay? Yeah. All right. Let's keep going. Does the following function has an inverse? Well, in order to have an inverse function to be defined, the function has to be 1 to 1. Okay? Because think about it. In this picture, let's say, do you see 5 map to 5? Yeah, 5 map to 5. And also -5 map to 5. But then when you ask, how do you find the inverse? Remember the inverse is you map the output back to the input. Oh my god, you have two input. Which one you should map to? So that's why the inverse function is not defined. Because you have two numbers, we don't know which one to map to. Therefore, in order to have the inverse function to be defined, the function must be 1 to 1. Okay, so let's say this is f. F is not 1 to 1. Okay, so therefore the f inverse is not defined. Okay, everybody? So, yeah, if this happens, let me give you an example. We all know that this is x squared. So y equals x squared. We know this is not 1 to 1. But however, you can restrict the domain, okay? Restrict the domain to be x squared equal to 0. Now, after you restrict the domain, okay, then you can define the inverse, okay? So actually, the inverse function is square root. So y equals square root of x, and that is the inverse function. So if you restrict, even though the function itself is not 1 to 1, but you can restrict the domain. So this piece is 1 to 1. Then a function is defined, right? How do you solve for x? See here, y equals x squared. Then you get x equals square root of y. And then you switch the x and y, you get y equals square root of x. Okay. So therefore, in order for a function to have an inverse, it must be 1 to 1. That is super, super important. Okay. And then example 5, check that these functions are inverse of each other by composing them in both possible ways. So composing them in both possible ways, we have f composite g and g composites f. Composition is not multiplication. Okay, so f composite g means f of g of x. So g of x is what? We plug in x plus 7 over 4. Yeah, g of x is x plus 7 over 4. And f of that means whenever you see x in the expression, replace x by this expression. Yes, everybody? So 4 times x. So 4 times now our x replaced by this x plus 7 over 4. And we have minus 7. So 4x minus 7. Erase the x and replace by this expression, x plus 7 over 4. Oh, do you see 4 cancel? And that's why we got, x plus 7 minus 7. 7 and minus 7 cancel. We have x. See? Composition. F composite G. We get x. How about G composite F? So this is G of f of x. F of x is 4x minus 7. Okay? g of 4x minus 7, then you look at the g, right? And whenever you see x in this expression, replace x by 4x minus 7. Okay, so yeah, this is the O expression. Now you erase the x and replace it by 4x minus 7. Oops, sorry. My hand sometimes just touch the zoom in and zoom out button. Okay. Now, do you see the 7 and the 7 cancel, right? We have 4x over 4, and the 4 cancel. We get the x. You see? F composite g of x is x. G composite f of x is also x. So f and g are inverse functions. So f and g are inverse functions. So far, so good, everybody? Awesome. So let's continue. Okay, in general, how do we find the inverse of a function? So here are the steps. First, you write y equals f of x. And then you switch the x and y. Solve for y. Okay, after you solve for y, that's the inverse function. So remember those 4 steps. Okay, let's use these 4 steps and do example 6. Okay, step 1, you want to write y equals f of x. So f of x is 3x cubed minus 4. Yes, everybody? And then step 2, switch the x and y. So when you see y, okay, change to x. When you see x, change to y. So far, so good? Yes? And then we want to solve for y. So solve for y. How do you solve for y? Add 4 on both sides. Then we get x plus 4 equals 3y cubed. And then divided by 3, yes? And then we take the cube root. Yes, everybody? Yeah, so take the cube root on both sides. You get, oh, that's x plus 4 over 3. Cube root is like raised to the 1/3, right? Because when you raise to 1/3 on both sides, 3 and 1/3 you multiply, you get 1. So that's why you get y to the 1. Yes, everybody? Awesome! So this is the third step. We solve for y. And the last step, okay, the f inverse is now x plus 4 over 3 to the 1/3. Is that okay, everybody? All right. And then example 7, I leave it as an exercise. Actually, we already show example 7 up here. So we show that square root of x and the y squared, when we restrict to the domain to greater or equal to 0, they are inverse. Yes. So, and then let's see, example 8. Yeah, we can do example 8. Okay, so step 1, set y equals to f of x. So minus x plus 4 over 2x plus 1. And then what is step 2? Switch x and y. So this is x, and then this is the y. Yes, everybody? Switch the x and y. And what's the next step? Solve for y. Yes, everybody? So solve for y with both sides multiply by 2y plus 1. That's minus y plus 4. Yeah, everybody? Okay, solve for y, which means we want to expand it and move all terms with y on one hand side and all the terms without y on the other side. So distribute it. So we have x times 2 times y plus x equals minus y plus 4. Okay, so we move all the y to the left hand side. So do you see this term has the y and this term has the y? We move to the left hand side. So that's why we add y on both sides. So this is 2xy. We order it. So 2xy and plus y. We have plus x equals 4. Okay, so yeah, we move all the terms with y to the left hand side and move all the terms without y to the right hand side. So we want to move the x to the other side, subtract x on both sides. So 2xy plus y equals 4 minus x. Is that okay, everybody? And then, do you see because all the terms on your left hand side has the y, we can factor that out. What's inside the parentheses? 2x plus 1. Yes. So, that's why y equals our right hand side divided by 2x plus 1. So, last step, this is the inverse function. 4 minus x over 2x plus 1. So far, so good, everybody? Yeah, so those are the 4 steps how we find the inverse function. Okay. Let's see. This problem. Okay, so answer the following questions. So, okay, we have f1. So see, f1, so 1, when we apply f, we get -3. Then what is f inverse of -3? 1. Yes, everybody? Okay, what is f inverse of f of 2? Do you remember when we composite with the inverse, we just get the number back? Yeah, so this is 2. Okay, yeah, so 2, and then we apply f, and then we apply f inverse, we just get it back. And solve the equation for t. Okay, first let's isolate the f term. So isolate it, we subtract 5 and subtract 5. Do you see we get f of 4t minus 3 equals 2 minus 5 is -3? Yes? And because f is 1 to 1, you see f of 1 is -3. So if f of this guy equals -3, this guy must be 1. Exactly. So yeah, we compare here because it's 1 to 1. So this has to be 1. 4t minus 3 has to be 1. How do you solve for t? Add 3. And then 1 plus 3 is 4. We divide it by 4. We get t equals 1. Okay. So here we're using the properties of inverse functions. Okay, very good. And then almost graph. Okay, how do we draw the graph of the inverse functions? So they have the property that because it switched the x and y. So let's pick some points. Do you see this point? This point is 1, 0. Okay, then for the inverse function, okay, let's plot some points. So this point is what? 2, 4. And let's say this point is 6, 9. Okay? Yeah, here we put 3 key points. Now, let's find the inverse function. Inverse function is like switch the x and y. So that's why 1, 0, and then when we switch the x and y, we get 0, 1. So this is 0, 1. 2, 4 is, so 2, 4 is right here. Then when we switch them, we get 4, 2. You see that, everybody? 4, 2, right here. So 4, 2. 6, 9. When you switch them, you get what? 9, 6. See, you get 9, 6. So then you connect those points together. So what property? Now you look at the graph and you look at the graph of f and the f inverse. Do you see they are mirror image about the line y equals x? Can you see they are mirror image about the line y equals x? This is the f. This is the sorry. This is the f, and this is the f inverse. They are mirror image across the line y equals x. Okay, so notice that the entire graph of the inverse function will then be the mirror image of f of x across the line y equals x. And this is so important. Okay, in chapter 4, we talk about exponential function and logarithm function. Our graphs, the inverse function, they are mirror image across the line y equals x. And last one, that is the, I leave it as an exercise, okay? So do it at home. And then on Monday, we'll talk about chapter 4. I know today we talked a lot, so please watch the recording and work on those exercises and review the notes, okay? Check the answers online. Do your homework. Ask me questions. Cheers! Have a good weekend! We try our best.